To find the Thevenin equivalent of an active circuit such as this one, we must leave the independent sources on or else apply excitation from an external test source. This means that the Thevenin equivalent cannot be found by the look-back method because that method requires that all independent sources be turned off. Turning off the independent sources deactivates the dependent sources as well and can result in a profound change in the input and output characteristics of an active circuit. Thus, there are two ways of finding an active circuit Thevenin equivalents. We can either find the open circuit voltage and short circuit current at the interface or directly solve for the interface IV relationship. So let's say, for example, we're asked to find the input resistance of the circuit that is shown here. Now, with the independent source turned off, that is I in is equal to IS is equal to 0, the resistance seen here at the input port is simply RE. Since the dependent source, beta IN, is inactive and acts like an open circuit. Now let's apply KCL, and we'll label this node A in here where the input source is turned on. Well, this yields that IE, the outgoing current, is equal to the incoming current, which is basically IN plus beta IN, and then factoring out IN yields beta plus 1 IN. Now, using Ohm's law, the input voltage Vin is equal to IE times RE. Okay, so the voltage Vn is just using Ohm's law to find the voltage across RE is simply IE times RE. Now we substitute IE and we have beta plus 1 IN times RE. Now we solve for Rn, which is basically the voltage input Vin divided by the input current IN. So we already solved for Vin right here, which is just beta plus 1 IN times RE all over IN. However, we see that the INs cancel in the numerator and the denominator, and that yields beta plus 1 times RE being equal to the input resistance when this dependent source is turned on. The circuit that we just analyzed is basically a model of a transistor circuit in which the gain, beta, our current gain, typically lies between 50 and 100. So beta here lies in between 50 to 100, and that the input resistance with the external excitation is basically beta plus 1 times RE, which is a lot different than RE without the excitation or the dependent source. The circuit that we just analyzed is basically a model of a transistor circuit in which the gain, beta, our current gain, typically lies between 50 and 100. So beta here lies in between 50 to 100, and that the input resistance with the external excitation is basically beta plus 1 times RE, which is a lot different than RE without the excitation or the dependent source. Just a quick note here, IN is found in this direction, which is the same direction as IS. So hopefully that clarifies this derivation of how we calculated the input resistance when the dependent source is actively turned on.